Hello everyone, and welcome to a captivating thin film series on semi-slides. I'm your enthusiastic host, Semi-Sherpa, and together, we're about to embark on an exhilarating journey into the realm of vacuum basics. Whether you're an experienced engineer, a curious student, or an aspiring professional in the semiconductor industry, this series is meticulously designed to equip you with a comprehensive understanding of the fundamental principles and wide-ranging applications of vacuum technology. From the basic concepts of pressure and vacuum to the intricate workings of semiconductor processes, vacuum pumps, pressure gauges, and more, we will leave no stone unturned. So, buckle up and prepare to delve deep into the captivating world of vacuum and semiconductor manufacturing. Get ready for an exhilarating adventure. Let's dive right in. Let's delve into the concept of pressure, an indispensable cornerstone for our discussion. Simply put, pressure denotes the force exerted on a unit area. This ever-present phenomenon takes on different nuances depending on its state of matter, be it solid, liquid, or gas. When we consider solids, pressure embodies the force exerted by the inherent rigidity of the material. Take a piece of wood as an example. Applying pressure to it means we're compressing the very molecules that comprise it. As for liquids, pressure is determined likewise by the force per unit area. However, its complexity is enhanced by factors like gravity and depth. A familiar manifestation of this is the increase in water pressure as we descend into an ocean's depths. Gas pressure presents a unique case. Given the high compressibility of gases and their propensity to occupy their entire container, the molecules within exert a force against the container walls. This is what we perceive as gas pressure. Gas pressure thus encapsulates the linear momentum of the individual gas molecules. An essential detail to bear in mind is that pressure is a scalar quantity, possessing only magnitude and devoid of direction. So, why is gas pressure vital in semiconductor manufacturing? Within the vacuum processes utilized in this sector, sustaining accurate gas pressure is of paramount importance. This pressure management enables the deposition of thin layers of material onto silicon wafers, providing the degree of control required to fabricate complex, nanoscale structures. Let's delve deeper into the topic of pressure, specifically focusing on the units of measurement used, Torr and Pascal. These units are primarily used to quantify pressure in the realm of semiconductor vacuum processes. Torr, named after the physicist Torricelli, is a unit of pressure based on an absolute scale. It's defined as 1 in 760 of a standard atmosphere, with the reference point being the pressure exerted by a column of mercury exactly 1 mm high at 0 degrees Celsius. On the other hand, the Pascal, symbolized as Pa, is the SI unit of pressure. It's equivalent to 1 Newton per square meter, N per square meter. Named after the French mathematician and physicist Blaise Pascal, it's used extensively across scientific fields. Additionally, there's the bar, which is equivalent to 100,000 pascals and is very close to the atmospheric pressure at sea level. The standard atmospheric pressure, ATM, is another unit, approximately equivalent to 101,325 pascals or about 760 torr. In the context of semiconductor vacuum processes, we mainly employ these two units, Pascal and torr. It's essential to accurately control and measure pressure in these units during these processes to maintain the integrity of the semiconductor manufacturing. Let's unravel our main subject by first understanding what a vacuum is. In simplest terms, a vacuum is a space where matter is absent, or where the pressure is substantially lower than atmospheric pressure. Its nomenclature stems from the Latin adjective vacuus, signifying vacant or void. But what is this atmospheric pressure we're comparing it to? Essentially, it is the force exerted by the atmosphere at any given point. Imagine it as the weight of an air column above that point, reaching out to the atmosphere's edge. This atmospheric pressure isn't static, it varies with altitude, giving us the atmospheric pressure profile. Starting from sea level, where it's highest, it decreases as we ascend. On top of Mount Everest, for instance, the pressure is merely about a third of sea level pressure. In the stratosphere and above, the pressure continues to dwindle, ultimately nearing zero in space. However, in the semiconductor industry, vacuum doesn't imply absolute absence of air particles. Instead, it denotes an environment where pressure is considerably below atmospheric levels. Unraveling the fabric of vacuum in semiconductor processes, let's focus on two key concepts: mean free path and collision frequency. The mean free path refers to the average distance a particle, such as an atom or a molecule, can move before it collides with another particle. Collision frequency, on the other hand, describes the number of collisions that a particle undergoes per unit time. For instance, at a pressure of 2 millitorr, approximately 0.25 pascals, argon atoms exhibit a mean free path of about 3 centimeters. To put it in perspective, an argon ion or atom can travel 3 centimeters on average before encountering another argon atom. When we consider electrons at the same pressure in the plasma, the mean free path with argon extends to 30 centimeters. Now, translating mean free path to collision frequency, if an argon atom has a mean free path of 3 centimeters at 2 millitorr, it implies that the atom, on average, collides once every 3 centimeters it travels. This collision behavior plays a crucial role in shaping the outcomes of semiconductor vacuum processes. The mean free path of a gas molecule depends heavily on the molecular diameter, temperature, and pressure. If any of these variables change, the mean free path will also change, and indeed this can be calculated using a direct or inverse proportional relationship, depending on the variable in question. For gases other than argon, or for different conditions of temperature and pressure, mean free path calculations can indeed be made using online tools or websites that take these variables into account. Viscous flow and molecular flow are two fundamental concepts in semiconductor vacuum processes that determine the gas behavior. Viscous flow occurs at higher pressures when gas molecules collide frequently, creating a sticky effect that leads to a slower gas flow. This flow regime is characterized by a shorter mean free path and a higher collision frequency. Turbulent flow is characterized by chaotic and irregular gas motion, with mixing and eddies in the flow. In laminar flow, gas molecules move in parallel layers with minimal mixing, resulting in smooth and predictable flow patterns. On the other hand, molecular flow occurs at lower pressures when gas molecules are widely spaced and experience rare collisions. In this regime, the gas molecules move in straight paths without significant interactions, resulting in a faster gas flow. The mean free path is significantly larger, and the collision frequency is lower. The transition between viscous flow and molecular flow happens when the mean free path is comparable to the diameter of the pipe or chamber. Understanding the characteristics and transition between these flow regimes is essential for optimizing process conditions in semiconductor vacuum systems. In the realm of semiconductor manufacturing, thin film deposition processes like physical vapor deposition (PVD) and chemical vapor deposition (CVD) hinge on the critical control of pressure to manage the mean free path. These vacuum systems are regulated by providing a consistent flow of gas, known as the gas flow rate or Q or throughput, with units typically expressed in standard cubic centimeters per minute (SCCM) or standard liters per minute (SLM). This represents the volume of gas supplied to the vacuum chamber every minute. Concurrently, to purge impurities and byproduct gases, pumping is implemented. The rate of this pumping, known as the pumping speed, usually noted in liters per second, signifies the volume of gas removed from the vacuum chamber every second. When the gas inflow and outflow reach a certain equilibrium, a stable pressure is achieved within the vacuum chamber. This pressure, referred to as the process pressure or working pressure, is the operating condition under which the deposition process is executed. CVD processes, which involve chemical reactions, generally operate at pressures around the Torr level. On the other hand, PVD processes, aiming to exploit long mean free paths, function at much lower pressures, usually at the millitorr level. Conductance, a fundamental concept in vacuum systems, plays a critical role in optimizing gas flow during semiconductor processes. Conductance, C, represents the ability of a vacuum system to transmit gas flow and is influenced by factors such as the diameter and length of the vacuum line. In the context of vacuum systems, conductance determines the flow rate, throughput, Q, between two pressure points, P1 and P2. It depends on the characteristics of gas flow, whether it is in the viscous flow regime or the molecular flow regime. In the viscous flow regime, conductance is primarily determined by the physical properties of the gas, such as viscosity. As pressure decreases, the conductance increases, allowing for a higher flow rate. In the molecular flow regime, conductance is influenced by the geometry of the vacuum line. The conductance is proportional to the diameter of the line and inversely proportional to its length. Understanding conductance is crucial for optimizing gas flow and achieving efficient vacuum performance in semiconductor processes. Automated pressure control is essential for achieving precise pressure regulation and maintaining stable pressure conditions in semiconductor vacuum processes. Closed-loop control systems continuously monitor the chamber pressure using pressure gauges, allowing for real-time feedback. Control algorithms analyze the pressure data and make adjustments to system components, such as butterfly valves and pendulum valves, to modulate the conductance and regulate the pressure. In full pumping mode, the pressure control system increases the conductance by adjusting valves into fully open states, effectively reducing the pressure. Conversely, in constant pressure mode, the system controls the conductance by adjusting valves into optimal states, ensuring a stable pressure level. Different process types, such as PVD and ALD using full pumping mode and CVD using constant pressure mode, employ specific pressure control strategies tailored to their requirements. Continuing our exploration of vacuum fundamentals for semiconductor processes, we turn our attention to an often overlooked aspect, base pressure. Let's consider a scenario where no process gas is intentionally supplied to the vacuum chamber undergoing the process, in other words, when the throughput, Q, is zero. Though the valve might be closed, preventing gas supply, several pathways could still permit gas ingress into the vacuum chamber. For instance, gas could infiltrate through micro-leaks around the chamber's joints or the closed valve seams, given the exterior pressure at atmospheric levels. There might also be instances of gas backflow from the vacuum pump, or gas desorption from the interior chamber surfaces. This unintentional gas presence, even when the input gas is zero, can contribute to what is known as the base pressure. The base pressure is the lowest achievable pressure with the current pumping speed, and it is desirable to minimize it to reduce film contamination during thin film processes. A high base pressure implies higher impurity ingress, even at operational pressure levels. Typically, the base pressure in thin film processes ranges between 1 × 10⁻⁸ to 1 × 10⁻10 torr. For reference, the lowest pressure recorded in the Guinness World Records stands at 7.5 × 10⁻15 torr. This equates to only about 25 gas molecules existing within a volume of 1 cubic centimeter. In semiconductor vacuum processes, the intricate and vital connection between base pressure and surface contamination significantly impacts thin film deposition. The base pressure represents the lowest achievable pressure in the system, directly influencing surface contamination levels. To understand this relationship, we examine the time required for gas contaminants to adsorb onto a surface and form a monolayer. This adsorption process is influenced by the system's pressure. As the pressure decreases, the time needed for one monolayer of gas contaminants to form increases. For example, at a pressure of 1 millitorr, it typically takes approximately 2.2 milliseconds for a monolayer of molecules to adsorb onto the surface. This duration signifies the time needed to achieve complete coverage by gas molecules. Additional examples include 4 seconds in high vacuum and 4 days in ultra-high vacuum, as monolayer coverage time inversely relates to pressure. These examples emphasize the importance of maintaining a low base pressure to minimize surface contamination during semiconductor vacuum processes.
In semiconductor vacuum processes, achieving optimal vacuum levels is crucial for successful operations. The base pressure, which represents the lowest achievable pressure, sets the foundation for vacuum control. To reach higher vacuum levels, specialized pumps are employed. The roughing pump, typically a dry pump, is used in the initial stages to rapidly reduce pressure and establish a rough vacuum. It is effective for moderate vacuum levels. As the desired vacuum level increases, high vacuum pumps, such as turbomolecular pumps or cryopumps, are utilized. These pumps offer higher pumping speeds and are essential for achieving higher levels of vacuum. Different vacuum levels require specific pumping systems due to variations in gas composition and pressure. For example, the roughing pump is suitable for establishing the rough vacuum, while high vacuum pumps excel at attaining high and ultra-high vacuum levels. However, in semiconductor vacuum systems, oil-sealed rotary vane pumps and diffusion pumps are avoided due to the risk of oil backflow and resulting wafer contamination. Optimizing vacuum levels and selecting the appropriate pump for each vacuum range ensure efficient gas evacuation, reduced contamination, and precise control during semiconductor vacuum processes. In semiconductor manufacturing, maximizing productivity by processing more wafers within a given time frame is a key objective. Let's focus on the importance of optimizing vacuum levels to achieve this goal. Efficient vacuum pumping plays a critical role in reducing cycle times and increasing throughput. The Pumpdown Curve illustrates the time it takes to reach desired vacuum levels. By minimizing the time required for evacuation, more wafers can be processed within a set time frame, enhancing productivity. To expedite the evacuation process, the rough pump, pump, such as a rotary vane pump, is utilized. It rapidly reduces the pressure, allowing for quicker transitions to higher vacuum levels. The 4-line valve and roughing valve control the flow of gas during this stage. To achieve higher vacuum levels, a high vacuum pump is employed, such as a turbomolecular pump or cryopump. These pumps offer higher pumping speeds and are crucial for reaching the desired vacuum levels in semiconductor processes. By optimizing vacuum levels and employing efficient pumping systems, semiconductor manufacturers can enhance productivity, process more wafers, and meet the demands of high-volume production. Base pressure, outgassing, and leaks are interconnected factors that impact contamination and process integrity in vacuum systems. Outgassing involves the release of trapped gases from chamber surfaces, leading to contamination and reduced vacuum quality. Leaks are unintended pathways for gas entry, causing increased pressure and compromised processes. To address these issues, techniques such as degassing through baking and in situ dummy processes are employed. Helium leak tests, including spray tests, are conducted to identify and seal leakage points. Optimizing base pressure, managing outgassing, and preventing leaks enhance purity and yield in semiconductor vacuum processes. Residual Gas Analyzer, RGA, is a sophisticated instrument used to analyze and monitor the composition of gases present in a vacuum environment during semiconductor vacuum processes. It plays a vital role in ensuring the quality and reliability of the vacuum system by detecting and quantifying residual gases that can impact process performance and yield. The RGA instrument consists of several key components, including a filament, a quadrupole mass filter, and a data analysis interface. The RGA's working principle involves the ionization of gas molecules using a heated filament. The filament emits electrons, which collide with the gas molecules, resulting in their ionization. Once ionized, the gas molecules are accelerated by an electric field and directed into the quadrupole mass filter. The quadrupole mass filter separates the ions based on their mass-to-charge ratio, allowing the identification and quantification of different gas species present in the vacuum environment. The data analysis interface receives and processes the ion signals, providing real-time feedback on the gas composition and concentration. By providing detailed information about the gas composition and concentration, RGA enables process engineers to make informed decisions and optimize process parameters. It helps in troubleshooting process anomalies and identifying sources of contamination or process inefficiencies. RGA aids in achieving higher process yields, improved device performance, and enhanced overall process control. The real-time monitoring capabilities of RGA allow for immediate corrective actions, minimizing the impact of gas-related issues on the production line. In semiconductor vacuum processes, vacuum pumps play a critical role in achieving and maintaining the desired vacuum levels for thin film deposition and other fabrication steps. Different types of pumps are utilized based on the required vacuum range and process requirements. The choice of vacuum pumps is crucial for maintaining a contamination-free environment and achieving the desired vacuum levels. Dry pumps, turbo pumps, and cryo pumps are particularly preferred for their specific advantages in semiconductor applications. Dry pumps, such as dry screw pumps or dry claw pumps, are the preferred option for cleanliness in semiconductor vacuum processes. They effectively evacuate large gas volumes, providing coarse vacuum levels without the need for oil lubrication. Turbo pumps, specifically turbomolecular pumps, excel at achieving high vacuum (HV) levels. With their high-speed rotating blades, they create a molecular flow that efficiently evacuates gases. Turbo pumps are oil-free, ensuring a clean and reliable pumping solution with superior pumping speeds compared to rough pumps. Cryo pumps employ cryogenic cooling to condense and trap gases, enabling the attainment of ultra-high vacuum (UHV) levels. By utilizing extremely low temperatures, cryo pumps create a cold surface that adsorbs and removes gas molecules, resulting in exceptionally low ultimate pressures. These pumps are particularly suited for contamination-sensitive processes in semiconductor vacuum applications. In semiconductor vacuum processes, the selection of vacuum pumps is crucial to ensure clean and efficient operations. Dry vacuum pumps, including dry screw pumps and dry claw pumps, are used for roughing pump or pump, offering significant advantages over traditional oil-sealed pumps. Dry vacuum pumps operate without the need for oil lubrication, making them ideal for maintaining a contamination-free environment. They employ advanced sealing mechanisms and innovative designs to achieve high pumping speeds and low ultimate pressures. Dry screw pumps are widely used in semiconductor applications due to their exceptional performance. They utilize intermeshing screws to compress gases efficiently, resulting in rapid pumping speeds and a clean vacuum environment. The absence of oil eliminates the risk of oil contamination and reduces maintenance requirements. Dry claw pumps are another type of dry vacuum pump commonly employed in semiconductor processes. They feature two claw-shaped rotors that rotate in opposite directions, creating compression and generating vacuum. With their oil-free operation, dry claw pumps offer reliable and efficient pumping while maintaining a contaminant-free vacuum environment. Dry vacuum pumps, such as dry screw pumps and dry claw pumps, play a critical role in semiconductor vacuum processes by ensuring clean and efficient pumping, thereby enabling the production of high-quality semiconductor devices. Turbomolecular pumps, commonly referred to as turbo pumps, are sophisticated vacuum pumps widely used in semiconductor vacuum processes. They consist of a rotor and stator arrangement, where the high-speed rotation of the rotor generates molecular flow and enables efficient gas evacuation. The rotor of a turbo pump plays a crucial role in the pumping process. It is equipped with precision-engineered blades that are designed to create a superposition of velocities with the gas molecules, effectively directing them towards the exhaust side of the pump. The rotor is supported by ceramic ball bearings and a rotor shaft, ensuring smooth and reliable operation. Additionally, turbo pumps often employ permanent magnetic bearings and safety bearings to enhance stability and prevent any unwanted disruptions. On the other hand, the stator in a turbo pump plays a key role in achieving efficient gas evacuation. The stator's surface is specially designed for diffuse reflection, which means it reflects gas molecules in a way that maximizes their chances of colliding with the rotor blades. This interaction between the stator and the rotating blades allows for effective gas pumping and the creation of high vacuum levels. Overall, turbo pumps combine the intricate movements of the rotor and the carefully designed stator to achieve efficient gas evacuation in semiconductor vacuum processes. The use of ceramic ball bearings, rotor shafts, permanent magnetic bearings, and safety bearings ensures smooth operation and reliability in demanding semiconductor manufacturing environments. Cryogenic pumps, or cryopumps, are crucial components in semiconductor vacuum processes, providing a clean and high ultra-vacuum environment with pressure below 10 millitorr. These pumps achieve efficient removal of various gases, including water vapor, inert gases like argon, neon, helium, nitrogen, and other gases such as carbon monoxide, oxygen, and hydrogen. Their cooling techniques ensure optimal performance without oil contamination. A multi-stage system in cryopumps consists of an 80K baffle and shield, a 15K cryo panel with charcoal adsorbent, and a cold head with first and second stages. The 80K baffle and shield condense gases, particularly water vapor, below 80 Kelvin, effectively trapping and removing them from the system. The 15K cryo panel plays a critical role in adsorbing inert gases like nitrogen, argon, carbon monoxide, oxygen, and methane below 15 Kelvin, ensuring a highly pure vacuum environment. Non-condensable gases like helium, neon, and hydrogen pass through the cryo panel and are adsorbed by the porous charcoal adsorbent, further enhancing the cleanliness of the vacuum. The cold head stages maintain low temperatures necessary for enhanced pumping efficiency. The first stage cools the system to temperatures below 80 Kelvin, while the second stage achieves temperatures below 15 Kelvin, creating an ultra-low temperature environment. This enables the cryopump to effectively condense and remove gases, achieving high vacuum levels and minimizing the presence of contaminants. Periodic regeneration is necessary for cryopumps to maintain continuous operation. During the regeneration process, the trapped gases in the charcoal adsorbent are released, allowing the pump to restore its high performance. Regeneration typically involves heating the adsorbent material, which causes the trapped gases to desorb and be expelled from the system. This process is vital for maintaining the efficiency and longevity of the cryopump, ensuring consistent and reliable vacuum performance. Pressure gauges are essential instruments in semiconductor vacuum processes, providing accurate measurements of the pressure within the vacuum chamber. Different types of pressure gauges are utilized based on their working pressure range and specific applications. An atmospheric reference gauge is commonly used in load-locked chambers to establish a reference pressure for transferring wafers. It ensures consistent atmospheric conditions during the wafer loading and unloading process. Convection Pirani gauges are employed for rough pump-down monitoring, measuring pressures in the range of 10 to the -3 to 10 to the -1 torr. They rely on the principle of heat transfer to determine the pressure. To monitor the pressure in the foreline of the vacuum system, thermocouple gauges are used. They provide measurements in the range of 10 to the -3 to 10 to the -2 torr, utilizing the thermoelectric effect. For precise process pressure control, capacitance manometers are utilized. These gauges cover a wide pressure range from 10 to the -3rd to 10 to the -10th torr and operate based on changes in capacitance. Ionization gauges are employed for monitoring base pressure. They can measure pressures as low as 10 to the -10th torr by ionizing gas molecules and measuring the resulting ion current. Capacitance manometers offer several advantages in semiconductor vacuum processes. Their high accuracy and reliability make them ideal for critical pressure measurements in various applications, including thin film deposition and etching processes. These gauges can handle a wide pressure range, from below atmospheric pressure to high vacuum conditions, enabling precise control and monitoring of the process pressure. Capacitance manometers are also known for their excellent repeatability and stability over time, ensuring consistent and dependable pressure readings. In contrast, cold cathode ionization gauges are specifically designed for measuring high vacuum pressures. They utilize a cold cathode as the ionization source, allowing them to operate in a pressure range from the lower end of high vacuum to the ultra-high vacuum regime. Cold cathode ionization gauges are robust and resistant to contamination, making them suitable for harsh environments encountered in semiconductor manufacturing. They exhibit excellent sensitivity and response time, enabling real-time monitoring of pressure changes during critical processes. Additionally, these gauges have a wide dynamic range and can accurately measure pressures in the presence of different gas species, including noble gases and hydrocarbons. The combination of capacitance manometers and cold cathode ionization gauges provides semiconductor manufacturers with reliable and comprehensive pressure monitoring solutions across a broad range of vacuum conditions. These instruments play a crucial role in ensuring process control, optimizing yield, and maintaining the quality of semiconductor devices. The vacuum pump market plays a crucial role in semiconductor vacuum processes, offering a wide range of pump types to cater to different application requirements. The market is projected to grow at a compound annual growth rate, CAGR, of 5.8% due to the increasing demand for semiconductor devices and advancements in manufacturing technologies. Key players in the vacuum pump market include Edwards Vacuum, Agilent Technologies, Bush, Pfeiffer Vacuum, and other prominent manufacturers. Thank you for joining us in this insightful session on vacuum basics, the foundation of semiconductor technology. Your interest and dedication to learning inspire us. Don't forget to give us a thumbs up, subscribe to our channel, and turn on notifications to stay updated with our latest content. In our upcoming episode, we will dive into the fundamentals of plasma, exploring its advantages and disadvantages and their impact on semiconductor production's productivity and quality. We genuinely appreciate your support and enthusiasm. Stay tuned to Semi Slides as we continue to shed light on the captivating world of semiconductor technology.